So yeah, we're the Deep Space Exploration Society, and tonight we're going to be exploring magnetic fields. So the word exploring means this is more descriptive. It's not going to be as much analytical, but a descriptive tour of some magnetic fields. And what's on the first page here is, a picture of the aurora over Norway. And of course, we can't actually see magnetic fields. So what we can do is see the interaction of magnetic fields with charged particles around them, and then we can see the what the magnetic field structure might look like. So we're going to be doing some of that. The itinerary is we'll spend a good amount of time in the heliosphere, and that's the whole region of space containing all the solar wind and the sun's magnetic field. The heliosphere extends roughly 123 AU. That's an astronomical unit. That's the distance between us and the sun. So it's 123 AU from the sun. And the job of the heliosphere is to shield the planets from interstellar radiation. Then specifically, we're going to be looking at the heliospheric magnetic field. And this is something that used to be called, if you look at an old textbook, it used to be called the interplanetary magnetic field, but now they call it the heliospheric magnetic field. I'll just call it HMF. And that's the magnetic field that extends out from the corona. It's blown out by the solar wind out from the sun's corona. Then if you have a rotating, a rotating magnetic field will induce a current. So there's also something called it's a structure called the heliospheric current sheet. And it's a ripple in the heliosphere created by the sun's rotating magnetic field. So we'll look at that. And then at the end, we'll spend just a little bit of time briefly looking at galactic magnetic fields. We can use pulsars to probe the magnetic field of the Milky Way. We'll show that, and then we'll look at some VLA images of other galaxies, magnetic fields around other galaxies. So to start, magnetic flux density, and I'm going to be using bold font B because B is actually a vector. So it has three components, X, Y, Z components, but we're just going to be talking about the total magnitude here. But so B is the SI unit Tesla. And so we'll use both Tesla and Gauss. And keep in mind, the magnetic field drops off as the inverse cube of distance from a dipole source. Other forces such as the gravitational field and light and gravity, they both drop off as an inverse square, but a magnetic field drops off as the inverse cube. So on this table, the scale on the left runs from 10 to the minus 12th Tesla to 10 to the plus 12th Tesla. And in the middle is the strength given in both Tesla and Gauss. And then the example. So the first one is half a nanotesla is a measurement. That's an actual measurement of the interstellar magnetic field taken by Voyager 1. The second one, 10 to the minus 9th, is, let's see, that's 6 nanotesla. That's the interplanetary magnetic field at Earth's orbit. So that at that distance from the sun, it's roughly 6 nanotesla. Then the Earth's magnetic field at the equator is 28 microtesla. As you go north, it increases, and at Haswell, it's 51 microtesla, or it was yesterday. So these, the Earth's magnetic field measurements are actually from the NOAA model in Boulder, because we don't have our magnetometer installed yet, but when we do, we'll be able to use the models to verify that we're getting it right. Then the middle one there, sunspots are roughly 150 milliteslas. Medical MRI system runs about 7 Tesla. The strongest human-made pulsed field that I could find runs about 2.8 kilotesla. And then the last three are pulsars. And let's see, the first one there is the 0.1 megatesla. Those are the millisecond pulsars. They're the old stable ones that are used to detect gravitational waves. The next one is our favorite pulsar. It's the brightest one in the Northern Hemisphere. It's B0329 plus 54. And it runs about a tenth of a gigatesla. And then the last one I have listed there is magnetar, and they're quite strong, and they show up in the teratesla range. Now, on these last three on pulsars, of course, we can't actually measure the magnetic field there. They're estimated using, so what we can measure on a pulsar is the pulse arrival time. We can measure the pulse duration, and we can measure the rate of change of the pulse, how fast it's slowing down. It's called the spin down rate. So we observe pulsars are slowing down, and that's due to the radiation loss from the pulses. And so using conservation of momentum, you can do some calculations and make some assumptions, and you can get an estimate of the surface magnetic strength at the equator on a pulsar. Then you got to realize, oh, the actual pulse is leaving from a region closer to the pole. Now, a pulsar is only about 6 kilometers in diameter, so it's small, but still a few kilometers is important on the when the field drops off with an inverse cube. So they estimate that the field strength of the magnetic field strength on a pulsar is actually 1 or 2 magnitudes higher at the pole than it is at the equator, but the equator is what's used as a so-called characteristic surface magnetic field on a pulsar. Anyway, that's just kind of an introduction to some of this range of the strength. Motivation for this, some of you, especially some of the hams, may often look at the site up at Boulder, the NOAA site called SWPC. That's the Space Weather Prediction Center. And they have these very handy solar wind and the coronal mass ejection predictions. And so when there's a flare, then you can look here and see, what if it might impact the Earth. On these plots, the sun is at the center, the Earth is the green dot, and the red and yellow dot are the stereo A and B NASA satellites that are parked out at L1 to provide us advance warning on incoming particles. And so I'd look at these, and I ran this one just a couple days ago. Last week we had several big flares, and I run this prediction up for today, and it always spirals out. And I never looked into it to wonder, I wondered why, but I never figured out why. So that's one of my questions we're going to look at today was why do these things spiral out like that? And then a related question is, how can a solar flare on the sun's western limb still hit the Earth? And basically the idea is a flare is radiation storm, and the storm consists of these high energy protons. How can it be funneled back to the Earth even though we aren't in the direct line of fire? And I circled in red here kind of a clue. It's these interplanetary spiral field lines. They're also called Parker spiral. And so that's what we'll be looking at here is how this happens. So we're going to start this tour here back in about 2010 in the heliosphere. This is from the Encyclopedia Britannica 2012, and this is a schematic of the heliosphere. It's got the sun in the center, the planets and Pluto, and then the termination shock. And between the termination shock and the heliopause is an area called the heliosheath. And Voyager 1 transited the termination shock in 2004, and then a few years later, Voyager 2 passed through it. So at this time, Voyager 1 and 2 had gone through the termination shock, but they hadn't yet actually exited or crossed the heliopause. So this was an illustration of where they were at then. And then 10 years later, NASA has this model. So in roughly 2020, they're showing, oh, Voyager 1 and Voyager 2 both have escaped the heliosphere. They've transited this thing called the heliosheath, and they've transited the heliopause. And so Voyager 1 went through this region in 2012 and Voyager 2 in 2018. And we'll talk about some of the data that they collected. They were still reporting data after they'd passed through here. They no longer are reporting because the little nukes they had on, I think, ran out. Of course, out there, they can't use solar power. So, but they did both report valuable data all the way through and out into the interstellar region. So we'll start by looking at a couple of these components I've mentioned. First is the heliospheric magnetic field. On this diagram, and it's kind of an eye color test. You'll see the red lines, there's a green line, and then these blue lines. So you have the sun here at the center. 1 AU means the Earth is out here on this dotted line. The Earth is out here. This is the sun rotating. Regions of opposite polarity. So we have red is one polarity and blue is the other, are separated by this green line. So the green dashed line is this current sheet we talked about, HCS, the heliospheric current sheet. It separates regions of opposite polarity. And there's kind of three regions here in this diagram. And the first one, the heliosphere, is where we live. We live out here at 1 AU. We live in the heliosphere. The rotation, so these magnetic field are connected onto the sun, and they call them foot points. It's not, footprints, but it's foot points is where the magnetic field line is actually attached to the sun. It stays attached there. But of course, the sun is rotating. And so out here in the heliosphere, the dominant factor is the solar wind. And that induces this spiral geometry that we see out here. This source surface is the coronal surface. So if you've seen a solar eclipse, you get to see the corona. The corona is hotter and it extends out quite a bit further from the sun. So at this surface, and it's roughly 2.5 solar radius, at this surface is where pressure dominates both the magnetic field and the flow of the solar wind. Inside of the corona, it's different. It's dominated by the magnetic field. So inside this region, it is not spiral. It's more chaotic. It's dominated by the magnetic field out to this edge. And it's called superradial expansion. It's also just called non-radial expansion. So out here in the heliosphere, it's a radial expansion. Inside, it is not. It's different. It's more complex with more vector components. And it changes all the time. It changes throughout the solar cycle. It's not static. So, and we know that just like Earth's magnetic field flips, well, so does the sun's magnetic field flips. So that's kind of an overview of the heliospheric magnetic field. Then we're going to use a model, and it's called magnetohydrodynamics. MHD, it's a big word. Again, in the old textbooks that I used to look at, it was called dynamo theory. The same thing for the sun. It was called dynamo theory, but now it's called MHD. But it's a very high-powered computer simulation of the flow of plasma and the magnetic field around the sun. And this heliospheric current sheet gets twisted into an Archimedean spiral. This was predicted by Eugene Parker in 1958. He was at the University of Chicago. Then when we started launching satellites in the 60s, this was one of the things they discovered. This was first observed by satellite in 1965. They did observe this actual current sheet. This is the sun here. These are the inner planets. Earth's here, and out here is Jupiter. So this is just the sheet out to Jupiter. We're here, and it's 6,200 miles thick here at the Earth. So it's not thin. It is very weak. It's 10 to the minus 10th amps per square meter. That's 100 nanoamps. So it's not strong, but nevertheless, it's measurable. It's there. And the extent of it, how far this sheet went, was verified by Voyager 1 in 2012 and Voyager 2 in 2018 as they transited the helios sheath. As they left the whole heliosphere, the measurements changed. The galactic cosmic rays and magnetic field increased, while the actual particles of solar wind from our sun decreased.
From the bedroom or from
Then just a reminder, and I'd forgotten this, but the solar wind streams off of the sun at over 1 million miles an hour. So it's streaming off very fast. It slows down as it gets out towards the end of the heliosphere, and we'll talk about that. Now, we're going to look at this current sheet a little bit more. And all the next several slides are taken from NASA Goddard. They have a whole article on something they call the Voyager heliosheath bubbles. So we're going to find out what those are here pretty quick. But the idea here is in the north, we have a magnetic field pointing towards the sun. So these are the red lines. You're going to see red lines they're pointing towards the sun. In the south, the red lines are pointing away. So that's the magnetic field. Opposite fields are separated by this current sheet. So we know, like we said before, rotating magnetic field generates a current sheet. And Roger and I even saw a quick demonstration of that at a science fair there on Saturday. There was a gal with a model, and she demonstrated that. This is a different scale here, but now, due to the tilt of the magnetic axis of the sun, just like Earth's magnetic pole is not lined up with the geographic pole, neither is it on the sun. So the magnetic axis of the sun is tilted, and that causes this current sheet to flap like a flag in the wind. So this flapping current sheet separates regions of oppositely pointing magnetic fields into sectors. They just call them sectors. And so I guess conceptually you can kind of see that what's going on here, but then you have to start wondering, okay, what's going on out here? It gets more complicated. So we're going to look at that, but before we do, we need to take a little sidebar and look at a different phenomena that'll help explain what happens out there, and that's something called magnetic reconnection. The magnetic reconnection is a process, a physical process that very abruptly converts the energy stored in magnetic fields to the plasma and thermal kinetic energy. So if the magnetic field is in a plasma, then it'll send off a big spark, a huge spark of energy. And magnetic reconnection is actually what generates the solar flares and coronal mass ejections that we see on the sun's surface. This is just a cartoon illustrating it. Then if you look at the sun, the current very large sunspot, AR 3590, is the largest sunspot so far of this current solar cycle. We're in solar cycle 25. We're nearing the peak, and we have a lot of sunspots, a lot of activity. This big sunspot can actually be seen without using a binoculars or telescope. Of course, you need to use your eclipse glasses or put on a welder's helmet or something to go out and see it, but you can see this big sunspot here without other power. Now, this is a sunspot that released 3 X flares last week. I think it like Wednesday or Thursday, there was, within a 24-hour period, there was 3 very large X flares. And this image is from SDO. This is the Solar Dynamics Observatory. And it shows this very unstable region of this sunspot. It's unstable because there's opposite polarities pressed together. So these regions of plus and minus magnetic polarity get pressed together, they get squished together, and then magnetic reconnection happens very quickly. And when that happens, lots of energy is converted and released, and that's where the solar flare comes from. Now, magnetic reconnection not only happens on the surface of the sun, it can also happen out at the edge of the heliosphere. And that's what we're going to talk about. So the big difference is magnetic reconnection on the sun releases a lot of power because there's very hot plasma there. It's very cold out at the far edge of the helios sheath, so it's different. So that's magnetic reconnection. I'm going to go backwards for a minute to this slide. So here's where we were. We were talking about this big current sheet, and then it's getting divided into sectors. So we introduced magnetic reconnection. Now we're going back to the current sheet, and whoops, I went ahead too much. Let me back up. We're going to this we're going back to the current sheet. And as the solar wind decreases past the termination shock, it starts slowing down. Those sectors squeeze together until they break up into this sea of, it's this foaming, it's nested foaming magnetic bubbles. And magnetic reconnection is what causes that. So that's why I took that sidebar for magnetic reconnection, is it causes these magnetic bubbles, and they're not small. They're on the order of 1 AU themselves, very large. And the magnetic field strength is like 1 nanotesla. And the job and what they do is they scatter incoming cosmic rays. And so this region of nested bubbles is carried by the solar wind north and south, and it fills in this region of the heliosheath. Now, what's interesting is if you looked at textbooks before Voyager, you would see something like this. This was the scientist's best view was they knew we had regions of opposite polarity, opposite magnetic polarity, but out here they thought, oh, it's probably some kind of a smooth laminar flow region and some kind of a boundary or barrier between us and interstellar medium. Well, this is what things look like after Voyager is because as Voyager went through this, it was actually kind of a bumpy ride for the magnetometer. The magnetometer, I don't know if you remember, and I don't have a picture of Voyager, but Voyager 1 and 2, they look kind of awkward because they have that one arm, they have one arm sticking way out. It's 43 feet away from the satellite equipment. Well, that's where the magnetometer is way out there. So it's getting pristine measurements. But as it went through here, the meter would go up and down. It'd go from positive to negative, and it'd go through zero. And they realized it was going through these charged regions. So they did a lot of changes to their models and theories after the Voyager data came in. And the next so this is all from NASA Goddard again, and the next one is a simulation. So hopefully the next slide, it'll be, it's just about a 60-second simulation, runs through everything I've been talking about and should kind of illustrate it. So there's the sun, the two opposite magnetic fields, the current sheet in between the magnetic fields. And then we're going to focus in on the current sheet out toward the edge of the heliosphere, out toward the edges where those sectors are, and it'll show a sector kind of breaking off and what happens with those bubbles. So these are magnetic fields just bumping and jostling each other and forming and reforming. All the while they're fending off cosmic rays. So hopefully that's kind of explained the heliomagnetic field, the heliospheric current sheet, and some of the so obviously they know a lot more than like when I went to school. They didn't have any of this, so it's quite interesting. But since we're out here at the edge of the heliosphere, let's just step into the Milky Way and take a quick look around at what we can find out about magnetic fields in the galaxy. So the magnetic fields around galaxies are roughly 1 million times weaker than the Earth's field. And there's two ways we can observe this. So we can observe cosmic magnetic fields. The first way is called Faraday rotation. Faraday rotation is if you have a radio wave that goes through a magnetic field, then that radio wave will get rotated. And the rotation will add either it'll add either a right-hand circular or a left-hand circular rotation, polarization to that radio wave. So we're looking for circular polarized radio waves. And the second way is synchrotron radiation. And synchrotron radiation comes about from magnet or charged particles that go in or through a magnetic field. They get twisted into spirals, and the speeds do have relativistic effects. And so these rapidly spiraling charged particles in a magnetic field generate their own radio waves. So these radio waves are observable. And first, we'll look at a pulsar. So here on the left is this is one of our plots. This is one of our favorites. This is pulsar B0329 plus 54 that we collected. And the idea here is pulsar radiation has net linear polarization. What that means is when the radio waves, when the pulse leaves the pulsar, it's linear. For the most part, it's linear polarized. And yet often when we receive it here, it has a circular polarized component. It might be circular to the right or the left of some magnitude. So we can use that rotation to estimate the average galactic magnetic field along the line of sight. So LOS is line of sight. We're going to use this thing called rotation measure. In this little formula here, the magnetic field strength B is 1.232 times RM is rotation measure divided by DM, and DM is dispersion measure. We've talked about dispersion measure before on pulsars. And this little equation, this formula is out of this new book, Fundamentals of Radio Astronomy. There's 2 volumes. One is on observational techniques, and then this one is the astrophysics. So a few quick facts about this pulsar. Its period is 714 milliseconds. It's roughly 3,400 light years away from us. As I said before, this is the brightest one in the northern hemisphere. We collect it often and almost every time we try, just to kind of use it as a quick check. It's circumpolar, and that means it's up all the time. We can always see it. It's up towards the North Pole. I'm sorry, towards the polar star. So the dispersion measure of this pulsar, dispersion measure is it's a measure of the electron density in the line of sight. So you can just think of a column between us and the pulsar going straight up. This column will contain a varying amount of varying density of electrons in the hydrogen cloud. So these hydrogen clouds are floating around, and there's so many hydrogen electrons in this column between us and the pulsar. And when the radio wave hits these electrons, then they get dispersed, meaning the higher frequencies arrive a little bit earlier. We correct for the dispersion when we're processing the pulsar data, but now we're going to use the dispersion measure in this formula. The dispersion measure is roughly an indication of distance. It's not, you can't directly correlate it to distance because it depends on which way you're looking, how thick the clouds of hydrogen are. But the dispersion measure is, the units are parsec per cubic centimeter. The values, the published values we get from Australia, from the Australia Telescope National Facility. It's called the Pulsar Catalog. The rotation measure, what we actually want is we want to know the rotation measure contributed from the interstellar matter, contributed from these hydrogen clouds. And yet we have an observed value. We need to subtract off our own ionosphere. So we have some observed value for the rotation measure. We need to subtract off the ionospheric contribution to that rotation, because there's also electrons in our own ionosphere that further can change the rotation. Well, and that's fairly readily available. There's TEC is the total electron count. There's models, you can get them from NOAA, and you can, and we get them down at Haswell. This is what the University of Texas instrument is measuring, is total electron count right there at Haswell. So use a GPS station, compare L1 and L2, then you can estimate the ionospheric contribution of the rotation measure, subtract that from your observed value, and in this case, an average value is minus 64.3 radians per square meter. Minus just indicates the direction. So we just plug those into our little formula up here. B is, it turns out to be 2.96 microgauss, or if you like Tesla better, it's 0.293 nanotesla. That's the value, but it's actually the electron density weighted average magnetic field along the line of sight between us and that pulsar. It's directed away from Earth. So the minus sign means it's directed away from Earth. We know it's just along this one line of sight. It's the average value because we don't know the exact details of the hydrogen clouds, but we know that average value. It's electron density weighted because we use the dispersion measure in the calculation. And that's all the dispersion measure tells us is the electron density, the average. So that gives us one value for the magnetic field strength in the Milky Way between us and the pulsar. There's another constraint, is that, as I said before, the magnetic field strength B is actually a vector with 3 components, X, Y, and Z, and we're just looking in one direction. So most likely the total value for B is larger than just in one direction, just in the line of sight. Nonetheless, this is what we use. It's called the characteristic field strength of that pulsar. So I thought that was interesting. That was easy enough to get the field strength for that pulsar. Well, what if you took all the pulsars and did that? Well, that's what these folks did here. So this map is a magnetic field map of the Milky Way using pulsar data. And what they did here, the red-pink regions show increasing magnetic field strength pointing towards the Earth. Again, they would have been using the circular polarization on those. The blue-purple shows increasing field strength pointing away from Earth. The points are, so there's points and squares here. The little circles, the points are 1,100 measurements from AT&F. So these are pulsars that just looked up the published value. And then the squares are measurements of 137 pulsar observations that LOFAR did they generated new values. They also refined previous values. LOFAR is a low frequency interferometer in the Netherlands. And so they focus on lower frequencies, meaning down in the 50 to 100, 200 megahertz region in there is where they operate, I believe. But they generated this map with some of their data, with the catalog data. And then you might wonder, well, all right, you got a bunch of pulsars, but how'd you get all these other regions filled in? Well, they did the same thing, the Faraday rotation, for extragalactic sources. So they took a whole bunch of extragalactic sources and generated kind of a filled-in region with the pulsars, showing the regions there. So that was one good use of pulsars. Now, so we said we'd look at Faraday rotation, and we also want to take a quick look here at some of the Milky Way views. So this is an image from Meerkat. Meerkat is another very large interferometer on the plains of South Africa. It's part of the SKA, the Square Kilometer Array. So this was a 200-hour data collection at 1.4 gigahertz, pointing directly towards Sagittarius A. Sagittarius A is the center of the galaxy. It's where they've imaged the horizon around that supermassive black hole right there at Sagittarius A. And this also shows SNR as supernova remnants. So it shows several supernova remnants around the center of the galaxy. There's a lot of chaos. It's very dynamic. But what was very interesting and totally unexpected was these very large magnetic arcs and magnetic filaments just showing up in this very dense region in the center of the Milky Way. So, with these radio telescopes, they are certainly finding more structure and more things that they didn't know. Then the last one, this is the last chart, is outside of the Milky Way. They took these images and they've learned that galactic magnetic fields help shape star formation, actually can help speed up star formation, magnetic fields. So what they did here is the magnetic fields cause synchrotron emission to be polarized. Yeah, that's what we said on the earlier slide. So what they did was fascinating. These are both edge-on galaxies, NGC 5775 here. It's edge-on galaxy. It's a Hubble image in the visible and infrared. So the red is kind of infrared, then the visible, that's all from Hubble. Superimposed on it is a VLA image from the VLA array down in New Mexico, looking for the synchrotron radiation in the radio. And that's what they have here. And so they see these very large magnetic field structures through the synchrotron radiation on these edge-on galaxies. So both of them are about the same. Another edge-on galaxy showing a lot of these magnetic fields in the radio. And you can't do this with a face-on galaxy. A face-on galaxy obscures all of these views, but edge-on galaxy, they can start looking at this. So this was done just not too long ago. So they're learning more and more about magnetic fields. And that's my last slide, if there's any questions.
Yeah, Dan, I was going to ask a question about the current sheath. The magnetic field makes a lot of sense to me, but the current sheath, I'm not so sure that does this mean you could actually measure a current in interstellar space? How do they measure this?
This was measured. So this current sheet in our heliosphere was measured by satellites starting in 1965. So they've measured the satellites. Here's the Earth right here. We have a satellite in orbit. It's parked here, but it's constantly measuring the current there, and they've been able to measure that. So they've confirmed this, and Voyager also confirmed the extent of it.
So this is spiraling out. This would be in motion, right?
Oh,
So
yeah.
an opening flower spiraling out
Yeah,
constantly, right?
yep. Yeah, this is just a snapshot on that simulation.
So
They
that
could actually measure that current sheet flow from 2 probes on a satellite. Is that how they did it?
or across an antenna.
They'll
No.
cross an antenna.
Okay.
So like in ham radio, if we measure current in an antenna, right? I would think this would work the same way, right?
Standing wave.
Yeah.
Yeah, I don't remember this being in the textbooks when I went to school.
I'm not sure whether they use probes or an antenna. You can also put up what's called Langmuir probes, and you can measure the current between them.
Mhm.
Dan, in your picture, you show Jupiter outside of that, or it's
It was just a cutout. It's basically like a cutout. That's just to give you a sense of the scale.
yeah.
But
I
the
know
current-
Jupiter has a huge magnetic field.
Oh yeah,
That Saturn even goes through the tail of it.
yeah.
That's how big the magnetic field is on Jupiter. But when you measure it on the surface magnetic field is so spread out because Jupiter's so big that it's actually smaller than the Earth's magnetic field because we're so much smaller per square unit.
Oh, I didn't. That's interesting. I knew that it had a very large one. I didn't know the strength of it. But you're right. It is very large. But yeah, it was just kind of a cutout, just to illustrate for scale.
Yeah, it probably interferes with some of that
Oh, I'm sure it does.
when
Yeah,
it reaches Jupiter.
yeah. I'm sure it does. And that's you know, they have Juno and some of the other satellites there now, and they're taking more measurements and more observations, and they're going back and changing their models all the time. They're learning more as we go.
Something bothers me about this business that entirely always has. They will cheerfully draw a magnetic field line going out and then stopping. They can't stop. Magnetic field lines are continuous because there are no magnetic monopoles.
Right, and that's why now they're talking about magnetic reconnection, because you're right, they don't stop, but they do reconnect and continue.
Oh yeah,
Poles.
they can actually cross and reconnect it. The field doesn't exist, and it's a picture of something, but it's
Yep.
and to cheerfully draw a magnetic field line going off into nowhere is just fake. It's got to come back. It's got to come back around and connect back to itself.
Yeah.
Well,
Somehow.
It's
what
kind of like
reconnection does.
gravity. It's kind of like gravity. It never ends. It's everywhere.
Yeah.
So
I was thinking about solar flares, though. You talked about this sunspot here that you have displayed, releasing 3 X-class flares. Now, I thought those were released when the magnetic field broke on a prominence.
no, it can't break. It can break, but it has to reconnect. It has to.
Oh yeah,
Magnetic field line has to be continuous.
it has to connect to something, but it would
It has
break.
to connect to itself. Do you understand? It has to connect to itself. And that's what keeps bothering me about this whole thing.
There's 2 poles.
Well, and that's what they're saying is when it reconnects here in a plasma, it on a very short time scale, it generates a huge amount of thermal and kinetic energy in that plasma.
Okay, but it's forming reconnect. The word reconnection is quite true.
Right.
What's happening is a magnetic line is breaking and connecting to itself again,
Mhm.
but in a different path.
Yeah.
It absolutely cannot be discontinuous.
Yep.
That's what also sprach Maxwell. That's right.
It can get very weak, but it's
Oh,
still
it-
present.
Yeah.
Well, no, but that's Now don't confuse the magnetic field lines with the magnetic field density. See, that's the other thing. For example, the magnetic field lines of the Earth's magnetic field go through the Earth and connect back to themselves north to south. But they can get extremely dense. They're extremely dense in your neodymium magnet, right? Close to the magnet.
Mhm.
But as they spread out, but they have to come back around and connect back on the south side. And when they do, the magnetic field line has to connect to itself through the magnet. And so the number of magnetic lines per square measure, whatever it happens to be, in God's units as revealed by the French, it's per square meter. The line has got to connect back to itself,
Mhm.
which is why when it goes into a magnetic medium like a bar of iron or a ferrite or the earth or a star or anything else, it still has to connect to itself.
Yep. All right, great discussion. I'm going to turn this back over to Myron for what's next.
One last question, if
Yeah.
I may. B, is that astronomically, is B the vector measured in polar coordinates to stay consistent with other astronomical coordinate systems?
So the choice of coordinate system is arbitrary.
It is. It is. I was just, you described it as X, Y, and Z, but
Oh,
I could say R and theta at the same time.
right. Yeah. I've just X, Y, and Z is just for illustration.
Okay.
Yeah, which is really neat. You can have the same magnetic field line that has to connect to itself, and you can look at it in several different coordinate systems on its way. I mean, it can drive you nuts if you really think about it.
All right. I appreciate